All right, welcome everyone online to the next installment of our DC, Maryland, Virginia section of the American Ceramic Society Spotlight on Ceramics. I'm very excited to be able to introduce Dr. Celia Chari today, who was really generous to adapt the theme of her presentation to the Halloween holiday. And she's going to give a really cool talk today on macabre materials across time. Dr. Chari holds a PhD in materials science from Caltech, where she worked with the Catherine Faber group. Since then, she's been working on some art history and preservation projects, where she's currently an MCH-Dogra Art Foundation Fellow in Conservation Science from Harvard University's Mapping Color and History Project. So with that, I'm going to give the floor over to Celia, who's going to give a talk, and then please come up with some questions in the chat, and we'll field those who are at the end of the talk. All right, here you go, Celia.
Thank you so much, Russell. So yes, as you've just heard, my name is Celia Chari. I'm a material scientist and also an art conservation scientist who recently moved to DC. And Russell was kind enough to ask me if I wanted to give this month's DMV Spotlight webinar. And knowing that it's the 31st of October, I decided to make it a little bit more thematic than usual. And I'm going to be talking about macabre materials across time, from toxic pigments to Manic Alchemists, and it's going to summarize some of the projects that I've been working on over the last 3 to 5 years. So I'd like to start off these talks that are more on ancient materials by talking about the evolution of materials across time. This example is the Venus of Dolny Vestanus. It dates back to 29 to 25,000 BCE. And it's really crazy to me to think that at some point there were people that molded clay, decided to fire it to create these ceramic figurines that were used mostly for ritualistic purposes. So this figure was used as a symbol for fertility. But of course, there are other types of more functional materials that have appeared across time. So blades for hunting, craters used for funerary purposes, uh, ceramics used for decorative purposes, manuscripts that tell stories and pass on knowledge from generation to generation, clothes that keep ourselves warm and allow us to explore different parts of our universe, ceramics that make the most efficient turbine engine systems, ceramics that make the most efficient electric propulsion systems, and even materials that make us into the most efficient golfers. So within all of these different examples, we see different material systems across time periods and cultures that were developed to meet different societal needs. In my research, I look at these material systems focusing on the relationship between synthesis, microstructures, and material properties to really understand how these materials were made, how we can optimize chemical compositions and microstructures, and how we can ultimately understand how these materials behave in terms of their properties, their performance, and their eventual degradation. So in today's talk, I'm going to be referring to 3 case studies that I've been working on in the past few years, but with a slight Halloweeny twist. So I'm going to start off by talking about toxic pigments. In this case, it'll be the preparation and the light-induced alteration of arsenic sulfides. Then I'll be talking about some evidence that I've been observing on the use of red figure pottery used in funerary rituals. And lastly, I'll talk about a really interesting case of an imprisoned alchemist, Johann Friedrich Böttger from the 18th century, and his creation of Europe's first hard paste porcelain. So starting off with the arsenic sulfides, this project took place as part of my postdoc at the Harvard Art Museums. It's work that I'm still continuing. And the formed in collaboration with the Mapping Color and History project. To start off with, I want to just briefly introduce the idea of toxic materials in artworks. There are a lot of different types of materials used. For example, there are lead-based pigments, like you can see from the yellow or from the white features of this Islamic manuscript. Apart from Islamic manuscripts, lead white is featured heavily in paintings from the 18th and 19th century for its opacity and warm tones and its whiteness. There's also the use of cinnabar or vermilion, that's a mercury sulfide that gives a deep red hue. And even pigments like emerald green are sought after for its vivid, bright colors, despite the fact that they're rich in copper and arsenic. For today, I'm going to be concentrating on other arsenic-rich pigments referred to as arsenic sulfides, that vary in color from yellow to red. These pigments have been used heavily in manuscripts in South Asia. So this is where mapping color and history comes in. And I have here an example where the yellow borders that you see are actually made of orpiment. One of the most common techniques for identifying pigments in museums is actually X-ray fluorescence. So based on color and elemental composition, historically there have been assumptions of what kind of arsenic sulfides are present. And there was the unfortunate um, common misidentification of assuming that an arsenic containing yellow pigment is orpiment, or an arsenic containing red pigment is realgar, without any additional analyses that can give information on structure like X-ray diffraction or Raman spectroscopy. In reality, there are many different types of arsenic sulfide phases, and this has been one of the things that I've been looking at. So an example is para-realgar, and also there's a really rare orange-colored arsenic sulfide known as bonazziite, so this beta phase that we see here. And bonazziite is actually the high-temperature phase of realgar, so you can either find it naturally in its mineral form, referred to as bonazziite, or structurally you can synthesize it by heat treating realgar. Despite the fact that bonazziite is so rare, we have identified it in the workshop of a traditional Indian painter. So you can see here in the video, this is how the painter, Mr. Babulal Marotia, is preparing the pigment by grinding and crushing these mineral chunks into a fine powder. So knowing that this rare mineral was found within this workshop in Jaipur, I decided to look into this more carefully and understand if it could be present in other manuscripts that we had been studying, just misidentified because of the past ways in which these materials had been identified. One thing to note about both realgar and bonazziite is that they're really light sensitive. They can change color when they're exposed to visible light. And this is because of a photochemical reaction that takes place that alters its structure completely. So red realgar and orange bonazziite can transform into this yellow pigment when exposed to just visible light. And this can cause issues in the field of art conservation because, of course, we want to preserve the artist's original intention as much as possible. And having such a huge color difference in a work of art could cause issues when it comes to the misinterpretation of colors that are being seen and just a lack of understanding of the original vision of the artist. From a more mechanistic perspective, the way that this reaction occurs is that with light, there's initially a slight oxidation of the arsenic sulfide structure, which releases a free sulfur atom that attaches itself onto the arsenic sulfide molecule, creating this energetically unstable structure that eventually transforms again into this different structure known as para-realgar. So para-realgar has the same stoichiometry as bonazziite and realgar. It's just a rearrangement of these arsenic and sulfur atoms that leads to a completely different phase with a different color. I've been interested in tracking the differences behind the kinetics of these reactions and understanding exactly how the realgar to para-realgar reaction differs from the bonazziite to para-realgar reaction. So to monitor this more closely, I've been using time-resolved Raman spectroscopy to be able to understand exactly how quickly these reactions take place. So here I have a setup of the experiments that I've been running over at the Center for Nanoscale Systems at Harvard. In a nutshell, we have our sample on the stage of the Raman microscope. We have a laser that is pointing directly at the sample, and these are tuned to different wavelengths. And this is to better understand whether it's specifically red light, amber light, green light, or blue light that is triggering this photochemical reaction. And then we have a Raman microscope system that is just collecting data using a 785 nanometer laser. And that these spectra are being taken every 2 seconds. So we have a clear understanding of how the structure is changing with time upon these exposures to light. Here are some examples of Realgar with the spectra as a function of time after or during the exposures to blue light, green light, and amber light. I didn't include red light 785 because there is no change in any of the arsenic sulfides that I've been seeing. So they are not susceptible to change when exposed to red light. But as you can see, green light specifically is the one that is causing the formation of para-realgar, given enough time for it to form. With bonazziite, we're also seeing the green light causes the formation of para-realgar, but there's also a noticeable increase in the peaks corresponding to para-realgar. With amber light and blue light, again, we did not see any change with red light. And both in realgar and in bonazziite, when they're exposed to green light, we can visually see how those pigments go from being red to more yellow in color, red to slightly more yellow in color. So we're visually seeing the consequences of the formation of para-realgar. As this I should say this relationship with green light exposures was found to be directly related to the band gap of these materials. Both realgar and bonazziite are semiconductors, and using photoluminescence, I measured the band gap and found that it was really close to that of the green light laser that we used. So this explains why we're seeing that is affecting it so much. The fact that we're seeing bonazziite also be susceptible to blue and to amber light is just a sign that it's energetically a lot less stable than realgar. So bonazziite itself is much more susceptible to transforming into para-realgar than realgar is. And this is something that we'll talk about later. As a sanity check, I did also look at para-realgar using the setup to confirm that we're not seeing any additional secondary reactions. And structurally, para-realgar remains as para-realgar during all of these exposures to different wavelengths. But visually, one thing that was really interesting was that the color of para-realgar does change when it's exposed to green light. The thing is that this color is not permanent. When you remove that laser source, the color will eventually go back to being yellow. So this, to me, just pointed out the idea that the excited state of para-realgar is causing this change in color. There's not another type of phase that's forming. It's just this temporary excited state that is looking a little bit more red. So not permanent, but still interesting. And I think it just gives us more understanding of how complex arsenic sulfides can be and how sensitive they can be to light when it comes to controlling their color. So how does this relate back to the artists that we were working with? Knowing that bonazziite is so sensitive to light, much more than even realgar is, I asked the artist that I was working with whether he noticed any differences when he worked with bonazziite. If initially working with it and applying that onto paintings, he observed over time that it turned more yellow, or if he didn't notice that at all. And I was surprised to learn from him that he had not noticed the pigment turning more yellow. So to understand why it was that he didn't notice that, we followed the way that he processed bonazziite over an 8-day long process. So starting off, as I mentioned before, he takes these chunks of bonazziite, he grinds them down, and with the addition of water and further grinding, you can start to see little yellow streaks and yellow globules start to appear. He actually removes them and continues grinding the pigment over and over, adding the binder directly to it. So he's basically creating the paint during this process. And as the days go on and a week passes, you can see that the ultimate pigment that he makes is yellow in color. And when I analyzed that final pigment and compared it to the original bonazziite, I could see that there were considerable amounts of para-realgar within this final paint mixture. So I think this explains why, as a paint choice, Mr. Marotia did not notice that this pigment changed color that much after being applied onto paint. It's because without even knowing it, during the preparation process of this pigment and paint, he was inducing that photochemical reaction, making a paint that was a little bit more yellow, orange in color than orange in color. And because para-realgar by itself can be sensitive to light and turn more orange with certain exposures to light, even if this is not permanent, you can start to see why artists work with para-realgar and treat it as a golden, orange, yellow color. So we have actually found para-realgar in some manuscripts. This one dates back to the 16th century, and for that little tree branch, we confirmed the para-realgar was present. This is interesting from the perspective of knowing that Mr. Marotia worked with para-realgar, essentially. It could be treated directly as an intentional choice by the artist. This isn't just realgar that was originally applied to be a red pigment that then faded into a yellow color over time. This could have been the intention of the artist. But there is this question of, is the para-realgar that we're observing derived from a mineral like bonazziite, or is it derived from a mineral like realgar? To look into this, I carried out a few light exposure tests where I painted out different arsenic sulfides, exposed them to light from a window, also to different lasers, as you saw previously with the time-resolved Raman. And one thing that I noticed is that you can actually track a difference between the para-realgars derived from realgar or bonazziite using Raman spectroscopy. So for example, in this graph, I have Raman spectra for realgar, bonazziite, and this is just a control of para-realgar that's I know has derived from realgar. And in blue, you can see the para-realgars after the light exposure. So in the case of para-realgar, it stayed the same. In the case of realgar, it turned into para-realgar. Bonazziite turned to para-realgar. But I want to draw your attention to these two peaks, the one at 230 and 272. One thing that I noticed repeatedly is that the ratios of those two peaks, of the intensity of those two peaks, can directly tell you whether that para-realgar came from bonazziite or whether it came from realgar. And I think that that has to do with the fact that bonazziite itself already has a peak at 272. So there might be some residual, maybe not completely reacted parts of bonazziite that remain, causing that peak at 272 to be slightly larger. So that's just something that a technique that I've been developing to be able to identify para-realgar that originated from bonazziite to tie it back to these customs and processing methods of Mr. Marotia. Because there might be more artists based in South Asia that also work with bonazziite as a main source for the production of para-realgar. To tie it back more to the toxic materials perspective, it is pretty crazy to think that artists, even contemporary artists, still work with arsenic sulfides and these heavy metal materials, but they are cognizant of the fact that they are toxic and they do work with them with the right ventilation washing hands after working with them too. So at least in that way, it's very different to how artists would have worked with these toxic materials back in the 16th century. So moving on to the next little case study. This was an interesting project that I worked on over the last year and a half that started off with a question from a curator, Susanna Ebbinghaus over at the Harvard Art Museums. This is a red figure crater that, as you can tell, has been through a lot. It's fragmentary, so it's been broken into pieces. It was found in a burial site, which brought up the question of perhaps it was included in some kind of funerary ritual. And unlike other type of red figure that you might be more familiar with, there's a considerable amount of discoloration. So some areas are grayer, some areas are redder. I'm going to go over the main observations that I made on this crater and how this ties back to its use in a funerary ritual. But before I do that, I wanted to first introduce to the audience how red figure is made, because I think all ceramists will appreciate this really complicated firing process that goes through a series of oxidation, reduction, and oxidation steps. So ultimately, what you're left with the red figure pottery is this layer of black gloss that is over a porous red ceramic. The red that you see in the final crater is just the ceramic substrate, and all of the block highlights are made of this black gloss. So how is this made? You start off with raw materials, and the composition of the raw materials of the gloss layer is very different to that of the ceramic substrate. The gloss layer contains large amounts of illite, so this is a potassium-rich aluminosilicate, and also iron oxides, while the ceramic contains other types of aluminosilicates, like kaolinite, and high amounts of calcite, as well as iron oxides. In the first oxidation step that you can see here in B, we see that the illite starts to decompose, forming a potash flux. And the iron oxides start to oxidize into hematite. So this becomes really red in color. In the ceramic, we see that the calcite of the substrate starts to decompose, leaving behind pores. And again, those iron oxides oxidize into hematite. Now in C, which is the step here, we kind of see the opposite. There's reduction occurring. So hematite reduces into magnetite and hercinite. And in the ceramic, we see the exact same reduction of the iron oxides. And after this step, the gloss becomes impermeable to oxidation. And this is because it essentially solidifies, trapping those black iron oxides within that gloss layer. In the second oxidation step, the temperatures are much lower than the reduction or the previous oxidation step, so they never quite reach temperatures high enough to soften that gloss. And that gloss remains impermeable to oxygen diffusion and traps those black iron oxides. Whereas with the ceramic, the body is still quite porous. So oxygen can diffuse into the substrate, reoxidize those iron oxides, creating a stark difference between that black layer and the red substrate. And that's really how red figure is made. In the case of the Bouzy-Gus crater, we started to notice some deviations to what we would typically expect from red figure. The first are these little regions here. So this red is in regions where we would expect to see black gloss. And instead of it being a layer of a glass trapping black particles, it seems to have trapped red particles instead. This is something that occurs during misfiring, so during the actual production of the crater. And this can be supported by the idea that we're seeing this throughout the crater. It's not just in some small sections that seem to be defined by the break lines. Instead, we see it all over the crater's body. And this could have either happened in the first oxidation step, if the glass trapped the iron oxides and solidified too quickly, and maybe the other reduction and oxidation steps were carried out at temperatures that were lower than they should have been. Or it could have alternatively been carried out in the last oxidation step if the gloss layer was not completely impermeable to oxygen diffusion, and we might have seen some resulting patches of red gloss emerge because of differences and, I guess, errors that occur during firing. This usually happens when in the kiln there's an uneven distribution of heat. Perhaps it's because of the placement, perhaps it's because of the actual firing that took place. Prolonged heating times could cause this too. So there's many different factors that could result in misfiring. On the other hand, there's a different type of degradation that we're observing, and that's shown here. So unlike those red patches, this discoloration of the ceramic turning beige is defined by those break lines. So this is indicating that the grain of the ceramic occurred after it broke. And this is where historic contexts are really important. And working with the curator, Susanna Ebenhaus, we learned that during these practices, a common thing would have been to break these craters directly onto the funerary pyre. So the crater itself would have shattered into pieces, and completely by chance, depending on where those sherds landed with respect to the burning body, it could have been more reduced by high temperatures or less reduced. And we see that there isn't just two options. There really is a gradient of different levels of reduction that we're observing, from the red ceramic to it turning slightly more beige and then more gray in color. So our main question that we developed, since this was the first instance ever reported of red figure being used in a funerary ritual experiencing these types of high temperature reductions, we asked ourselves, is the hematite from the ceramic reducing into black magnetite and hersenite? And is this because of the funerary pyre? So to try to answer these questions, we carried out synchrotron radiation experiments, mostly X-ray absorption spectroscopy, to try to understand the oxidation states and speciation of iron across the ceramic and also the gloss layers. We were fortunate enough to be able to get some mineral samples from Harvard's Mineralogical Museum, including hersenite, magnetite, hematite, magamite, and also tektite. And we compared the Zane spectra of these iron oxides directly to our samples. So first, starting with alterations from misfiring, this is where we're seeing that the regular black gloss over the red ceramic is oxidizing into this red gloss over the red ceramic. We saw that when it came to the ceramic, in both cases, they're rich in hematite. And then with a black gloss, the original black gloss was rich in hersenite and also contained signs of containing magnetite, while the red gloss is rich in hematite. So here we have evidence for the oxidation of the gloss, while the ceramic looks similar in both cases. We proposed mechanisms for this oxidation of the black components, so the hersenite and magnetite particles within the black gloss, and it's listed here. And as a second point with the funerary pyre, and this is where the ceramic substrate itself has reduced, but the black gloss appears to be the same. We see that the ceramic starts to contain signs of hersenite and magnetite. So this is confirming what we initially thought, that there is a reduction of the ceramic and that it is because of the creation of hersenite and magnetite, whereas the black gloss stays the same. So gloss is similar, and in this case, the ceramic has reduced. And here are some proposed mechanisms of how that happened. So the iron oxide, the hematite would have reacted with neighboring alumina components within the ceramic. So even though the gloss is similar according to the Zane's analyses, we wanted to look into this question a little bit more closely using more localized studies with FIB-SEM and STM-EDS. So we cut out different samples from these gloss layers. So either the black gloss from the red, black gloss from the pyre. And we looked at these samples with TM, and also we did eels mapping to be able to look at the oxidation states of each individual particle within the gloss layer. And we found these general conclusions. The black gloss after the pyre has magnetite, hersenite, and also ilmenite. So ilmenite was not something that we found with Zane's, also because we did not have an ilmenite reference in our studies. So this was a new observation. And then with this is actually similar to what we saw with the black gloss on the red ceramic. So in both cases, we're seeing magnetite, hersenite, and some ilmenite. The main difference between the two is actually the particle morphology. So initially, in the original gloss, we see these small particles, and they're distributed evenly. After the pyre exposure, we see much fewer particles, and they're larger in size. So a thought is that during the high temperature reduction, there could have been some particle growth that led to differences in the morphology. So in a way, there were alterations in the black gloss because of the pyre exposure. They're just so small, like on the within a micron by a micron visibility, that it's not something that is visible more on a macro scale. It's kind of insignificant when it comes to the actual quality of the gloss layer. But nevertheless, there are some differences just on a much smaller scale. With the red gloss, we're seeing also that there are larger particles that are forming because of the misfiring. So this is also a sign that the misfiring was due to prolonged firing times that allowed those particles to grow larger. And our analyses of the elemental compositions supported what we had seen previously, that there is a lot of iron oxide directly from hematite within the red gloss, and that it's much higher than what we saw with the other black glosses. So there are two different things happening. There's the misfiring from the actual production of the crater. There's the exposure to the pyre from how this crater was then incorporated into a funerary ritual. But there is a third different reason why this crater is altered, which I have not mentioned up until now. There are some signs of alteration from the burial conditions. So I'm laying this out now because it is a very complicated object, and it might seem like all of these different pieces are connected, but they're not. And it's only really with advanced characterization techniques that you can start to decouple all of these different factors that could have affected the final state of the crater. So I won't go into it with too much detail, but with the burial conditions, so that you have an idea of what I mean, there is a depletion of silicon and potassium at the very surface of these gloss layers. And this could be due to the local humidity or acidity of the soils in which these fragments were buried. So this is not something that is dependent on whether those fragments were misfired or exposed to the pyre. All of the fragments, no matter what condition they had, experience this kind of silicon and potassium depletion. So this is a completely different third alteration mechanism that's occurring. So yes, a little gruesome to think about this crater being used in a funerary pyre, but it's really interesting to see that, this is a part of the lifetime of that object, and now it is physically a part of the object too. So I'd like to finish with the last case study. And this is actually going back to work that I did during my PhD. So the previous two talks were all on research that I conducted at the Harvard Art Museums. This is a project that I carried out at Caltech in the lab of Kathy Faber. And this was a project that I think she started while she was in Northwestern. So it was ongoing for many, many years. And when I was a grad student, I finished it by adding some reconstructions and that I'll mention in this talk. But it's a very interesting story. I don't know if you've ever heard of the inception and I guess the creation of the Meissen Manufactory, but it all started because of one man. So his name is Johann Friedrich Böttger. He was born in 1682, and he's known for being a German alchemist that helped develop the first European hard-paste porcelain. He originally trained as an apothecary, but Böttger became fascinated with alchemy, and he claimed that he could turn base metals like mercury into gold. And this is something that caught the attention of Augustus the Strong, Elector of Saxony, who had a notable passion for luxury and the finer things in life, and who was interested in Böttger's so-called ability to produce gold to further finance his passions. So, imprisoned under court supervision to pursue this goal, Böttger instead collaborated with the notable scientist Ehrenfried Walter von Schirnhaus, and around 1708, they succeeded in producing Europe's first true porcelain in Meissen. Now, it should be mentioned that Augustus the Strong was particularly fascinated with porcelain, often referring to it as white gold. And he amassed collections of Chinese and Japanese porcelain in his palace. Böttger and Schirnhaus's breakthrough not only ended China's centuries-long monopoly on porcelain, allowing Augustus the Strong to launch the famous Meissen Manufactory, but it also gained Böttger his freedom from being executed, but not from being imprisoned. Despite the scientific achievement, our little alchemist friend remained confined, overworked, and ill of health until he died at just 37 years old. So it was quite an unfortunate life for Böttger. But on a lighter note, it's really interesting from a ceramics perspective to compare the composition of porcelain from the Far East to that of Europe. It's quite intelligent what Böttger and Schirnhaus ended up doing. So to create the porcelain bodies, Chinese craftsmen mixed white kaolin clay with finely ground China stone as their temper. And during these high temperature firings, the mineral components of China stone reacted with kaolinite to form a viscous liquid phase, which became a glassy solid upon cooling. And this image here shows these rounded quartz particles that result from this process within this silicate matrix, and you can see the little acicular molyte crystals. In contrast with European porcelain, the earliest bodies, which are referred to as Böttger porcelain, combined powdered alabaster with Schnorr's earth. And Schnorr's earth contains kaolinite, but it also contains quartz as the temper and feldspar as the flux. And this combination of ingredients for the porcelain paste resulted in porcelain bodies that were richer in calcium. So this was smart because it meant that the firing temperature for porcelain decreased significantly to what was used in the Far East. So it was easier to produce in a way. And yeah, it's through trial and error, these recipes were refined within Meissen. Initially, it was a struggle to create polychrome decorations at the Meissen factory. However, by the 1720s, a lovely color palette started to emerge. And you can see here what I mean. There's some cobalt blue glazes. There are glazes that are black with manganese oxides, glazes that are red with red iron oxides. But for today, I'm going to focus on these two purple glazes that I've shown here. Purple of Cassius and Böttger luster, named after the alchemist. These glazes caught our attention for a number of reasons, the most important one being that they both contain gold, with X-ray fluorescence that is, as I mentioned before, a very common technique for identifying elemental compositions in artworks. It was noted that there were high amounts of gold in the luster glaze and in purple of Cassius. But the optical properties of these glazes are quite different. In one case, we see iridescence. So with the lusterware, depending on the angle at which you're looking at the glaze, you can see colors that range from brown to purple to gold. While with purple of Cassius, the color is a lot more matte and it's more vivid, more purple. So to look into the origins of these optical properties more closely, we used FibSEM to prepare little samples for TEM. And to give you a perspective of the cross-section of this glazed porcelain, these TEM images that I'm about to show are really just describing the top of the overglaze enamel. And here we can see the colorants that are responsible for Böttger, luster, and for purple of Cassius. And we see that they're really close to the surface. So using STM EDS, we looked at the elemental composition of those particles and also of the glaze that was directly surrounding them. And we confirmed that the gold that we had been detecting with X-ray fluorescence is originating from these little gold spheres that are distributed within a lead silicate matrix. In the case of Böttger luster, we have really large spheres, but also some smaller ones, while with purple of Cassius, we have pretty uniform nanoparticles of gold. One thing that I want to draw your attention to is the content of tin. There is no tin within the luster glaze, but in purple of Cassius, directly surrounding these gold nanoparticles, there is the presence of tin, even within the lead silicate matrix. And that's something that I'll mention in a little bit. So we carried out some statistical analyses to see the distribution of nanoparticle sizes in both the luster glaze and in purple of Cassius. And we can see that with purple of Cassius, the nanoparticle size is really uniform. And this size that we're seeing on average is really similar to the nanoparticles that we would expect to see in ruby or cranberry glass. So these historic glasses are essentially colloids of gold nanoparticles within a tin-rich matrix. And they're prepared by mixing gold salts with tin that acts as a reducing agent, allowing for those gold metal nanoparticles to nucleate and grow. And in a similar way, purple of Cassius might have been synthesized and prepared using tin as a reducing agent, which could explain why we're seeing such a localized presence of tin directly surrounding those gold nanoparticles. In contrast, the distribution of sizes that we're observing with the lusterware is much more similar to what we would expect for other types of luster. Up until this point, this was the first publication that looked at luster being produced out of gold nanoparticles. Before that, luster was typically, or I guess more common forms of lusterware were made out of silver and copper nanoparticles. So the literature was all based on these studies on silver and copper nanoparticles. Some methods for preparing these luster glazes involved first firing a glaze, adding salts, metal salts directly onto it, firing it again at a slightly lower temperature, just enough for those salts to diffuse into the glaze and then nucleate into nanoparticles. And this is all being fired within reducing environments. But this had not actually been tested or seen with gold luster. So this is why the recreations were really important. And this is something that I worked on during my PhD. So I referred to several sources for being able to develop these purple luster glazes. I don't want to describe it as recreating Böttger luster because we never really will be able to completely recreate it. We don't have the same firing, the same furnaces, the same conditions and ingredients that would have been used originally in Meissen, but I do want to describe it as recreating purple luster with gold nanoparticles. The references and resources that I used to develop these recipes came from different sources, including Kingery and Vandiver. Kingery did a lot of work on reconstructing Böttger porcelain and clear glazes, and this is a ternary phase diagram from his book, Ceramic Masterpieces, and the compositions shown in black stars are the exact compositions of my recreations of porcelain and the clear glaze. I also refer to ternary phase diagrams for lead aluminosilicates and recipes that originated from Meissen. This was very useful, and it's very fortunate that around a similar time, so this was maybe 6 or 7 years before I started working on the recreations, there were translations that were published by Nicholas Zumbuliadis. He went to the Meissen records and translated the preparation and the recipes of Böttger luster from German into English. And that's what I used for a lot of my deeper understandings of how luster is made. So it starts off by reacting gold leaf with aqua regia to form these gold salts. These salts are then converted into the highly explosive gold hydrazide that easily reduces into metal gold and can grow into nanoparticles. Gold hydrazide is very sensitive to air and to moisture. So it's thought that this is mixed intimately with the frit and then applied directly onto the surface just to minimize the contact of these salts with air. In the Faber group, we did not want to work with gold hydrazide. So for my gold salt, I worked with gold chloride, which also worked as a source of gold. It was just different to what the original luster could have been. But I'm happy to not have worked with gold hydrazide, I will say. So this is the purple luster that I recreated. These are different versions of it. The most successful one is shown here in blue. And this is just a cross-section view showing that very close to the surface, we see the presence of these gold nanoparticles. Now, within the glazes that I produced, the sizes of the gold nanoparticles also varied. You have ones that are larger, ones that are smaller, but the overall average is greater than what we saw with historic lusterware. So yeah, these are just differences though, based on different materials and actual synthesis conditions. But it's still within the same realm of nanoparticle sizes that results in the same optical effects. And this is the next section. I won't go into the details. I'm running out of time, so I'm not going to go into the details of the modeling. They're all listed in the paper if you want to read them more carefully. But the main conclusions from this is that in Böttger luster, we have both these larger nanoparticles and the smaller ones. The small ones contribute to purple through Mies scattering, while the larger ones create a disordered nanoparticle array that cause these interference effects that make the glaze look more iridescent. In contrast with purple of Cassius, we only see these small nanoparticles because of the control and particle growth that we're observing when tin is present. There's much more of a uniform size. And because we're missing these larger particles, we are not seeing any array interference effects. So despite, or I guess with the presence and being able to use these advanced characterization techniques to look at these glazes much more carefully, we can start to reveal the mechanisms behind those glazes that Böttger produced during his imprisonment. And it's just interesting to be able to, in a way, go through the same trial and error in the preparation and reverse engineering of his porcelains and his glazes in a way that he would have too, just with much less pressure than what he was under at Meissen. And with that, I'll just summarize these examples. So in this talk, I hope to have convinced you that material science plays a really important role in the study of ancient materials. And it's really by looking at synthesis, microstructure, and material property relationships that we can start to understand the evolving and sometimes sinister role of materials in society. And there are many people I would like to thank, especially my PhD advisor, Catherine Faber, my postdoc advisors, Narayan Kandakar and Catherine Ehrman at the Harvard Art Museums, my current advisor, Gina Kim at Harvard, and also the Dogra Art Foundation for their ongoing support of my research. And thank you so much for listening. I'm happy to answer any questions.
Celia, thank you so much. That was a very, very great talk. I like the art history that was put in there too. That was really refreshing. So we're gonna open this up to questions now. Anyone that has one, please type it into the Q&A. So we'll start with Keith Bowman, who's a professor at UMBC. He says, thank you for a great Halloween treat. This is a selfish question. Next semester, I am teaching for the first time a course on materials characterization for seniors and grad students in a mechanical engineering program. It is essentially all the acronyms, TEM, EDS, FTIR, XRD, XPS, etc. Do you have a recommended best resource for materials characterization in your research context?
Is it book specifically for these examples in cultural heritage or just in general? Uh, if it's just in general, I would say that for me, my resources have been just training. This is something that through practice I've learned in different institutes that I worked in. I don't know if there's a single book that I refer to. It's mostly just the people that I work with and the places I work in.
Keith, you might just have to get Celia in for a guest lecture for that class. Carolyn Prima says, thank you. That was an excellent talk. I'm going to add a question that I had, which is, could you kind of just walk us through, you're working with these priceless artifacts. What's the permission structure look like
Yeah.
for even getting to handle these things, and how do you fib out a cross section of that's that priceless? You know, we all, I think, watching know how we would do that with a sample that we don't really care about, but for something that you can't you can't mess up
Yeah.
on. You know, how are you carbon coding priceless artifacts so that you can fib them out, or what's that look like?
Yeah, no, it depends. Okay. In general, for sampling, it is very museum dependent. The nice thing about the Harvard Art Museums was that it is a university museum, so there is a lot of interest in cross-departmental collaborations. Obviously, you cannot sample every single object, and you can't always, it's very difficult to actually bring in objects to research institutes where you have the instrumentation to do this level of research. So typically, what I've done, at least I can only talk about what I've done, uh, with those samples that we take in the museum, we prepare cross sections out of them and then bring those to places like the Center for Nanoscale Systems. And that we can carbon code, that we can do everything with. So it's not the actual object, it's just little samples from the object.
Okay.
Yeah, and permissions for sampling really do vary between museums and between curators. So there is no rule of thumb. It really is just who you work with.
Is it the case then there's kind of I don't know, like working pieces then that are shared between lots of labs that are kind of for that purpose of doing the type of work that you do on them? Are there like kind of like
Yeah.
limited number of like examples of things that get shared and passed around for this type of work?
So a lot of museums have the instruments that they use most regularly in-house.
Mm.
So for example, we worked very closely with the Museum of Fine Arts Boston. They have their own SEM EDS. They have their own Raman system, their own XRF system. So for them, they can prioritize their work within their own lab. At the Harvard Art Museums, we also have some instruments that we use very regularly. What happens is that this is kind of an outlier example of museums in this country because it is tied to Harvard.
Mhm.
There is that added access to facilities within the university. But that is really uncommon. That is not something that you see in most museums. So they
Right.
depend on the instruments that they have in-house.
Okay. Thank you. All right, so Keith got back to us and he said he's gonna share this really good presentation with his class as a start. And so because we have a little bit we have a couple minutes. We talked about this before your talk started. I wanted you to elaborate a little bit more on this mapping color and history project
Yes.
that you're currently working on.
Yeah. Okay, so let me see. This is from a different talk, but basically the idea behind this is that historically minerals and I guess materials that would have been used to prepare that were technologically important to prepare ceramics, to prepare glazes and metals would have been mined. There are different types of minerals that are used for pigments also. Here I just have an example. In this manuscript, those are pigments that were used and identified exactly for that manuscript. The purpose of the Mapping Color and History project is that we're trying to figure out more information about the evolution of these pigment choices throughout time. So knowing that minerals are so important, one of the resources that might pop into mind are websites like Mindat. They give information about localities and of ores and compositions of minerals throughout the globe. And that, for the most part, is absolutely true. It's a very important tool that we use constantly for our research from all over the world. But when it comes to South Asian art, there is a lack of information on ores that are present throughout the subcontinent. We're trying to fill in those gaps through a different perspective by looking at artworks, identifying compositions and trace element distributions from artworks with known time periods. So we know that these artworks were produced in the 16th century. We know that they contain pigments that have trace elements that are a little strange, but we're adding those to the database to build a broader perspective of the occurrence of these different mineral pigments. So this is a screenshot from the website. We have the interactive maps that allow you to be able to filter things out by geography. We also have timelines. So if you're only interested in 16th century or 15th century artwork, you will only see the search results of artworks from that time period and that geographic location. And it just gives you a broad idea of the types of materials that would have been used throughout time. One of the things that we have been doing that's pretty cool is seeing the evolution of the use of different colors. So, for example, with yellows, pigments that would have been naturally occurring, so like plant-based yellow pigments or arsenic sulfides like orpiment, were replaced by pigments like Indian yellow, and then eventually replaced by pigments like chrome yellow. And these are observations that have been made before, but never with the statistics, or I guess the quantified data to back it up. Because this database collects so much information from different artworks, not just at the Harvard Art Museums, but in collaborating institutions across the globe, we have those statistics to back up these claims of the evolution of pigment use and the occurrence of different types of pigments. One example that I told Russell about before the talk is we've been finding orpiment within manuscripts that contain high amounts of barium. I was looking through Mindat to see if there are any known ores, at least that are recorded, that have orpiment with that kind of high level of barium impurities. That's not something that I found through Mindat, but this is a record that is tied to an existing artwork that is a sign, I guess, evidence that at some point throughout history, these ores were used. So I'm hoping to collaborate with mineral informatics people to be able to work on re-understanding and I guess rediscovering some of these ores that might have been lost throughout time.
What a cool, fun project. Thanks a lot for elaborating more on that. All right, so with that, I think that puts us up at the end of the lunch hour. So again, I just want to thank you, Celia, for giving a really great talk. I think people are going to be interested in finding this online and revisiting it. And so with that, thank you everyone for attending today. We are going to be on a brief hiatus with the holiday season coming up, but look for some more Spotlight on Ceramics webinars in the 2026 beginning of the year. Thank you all and have a good weekend. Thanks,
Thank you.
man.
Bye.
Bye.
Bye.